So thank you very much, Sandra. It's very kind of you to make such kind words for presentation, and it's a great pleasure to be here this morning. And what I thought I'd do this morning is talk a little bit about some work we've been doing on multiphase jets and plumes. So these are very large turbulent flows where there are particles or bubbles which have a big effect on the buoyancy of the flow and thereby impact the overall large-scale dynamics of the flow. And is there a stick or a pointer? That's great. Thank you very much. So on this slide, I've just put a few pictures up. These are very large multi-phase flows associated with blowouts in hydrocarbon and oil well development. So this is a well on the seabed, and it shows you a stream of oil and gas coming out and breaking up into small droplets, which forms a very large plume. This is a blowout of a gas field where there's the gas has reached the sea surface. This is the rig. So this is a very large area, several hundred meters across, where gas has reached the sea surface, spreads out, and we'll have a look at what happens to some of the fluid in these sorts of events. There's also some interesting effects of multi-phase flow. This is from the Fukushima incident in 2011, where following the failure of the reactor, a large cloud of particles rose into the atmosphere, and we're also interested in where those particles rise. And of course, in volcanic problems, there's a lot of interest in understanding when a volcano erupts, how high the ash rises in the atmosphere and what controls how that ash then disperses. There's some very interesting dynamical effects associated with separation of the particles and the air being carried, or that's carrying those particles. But I wanted to start off today talking about a different problem of deep sea mining and talk a little bit about some of the sediment suspension that may occur and its potential environmental impact. So I guess this is a map of the world, and here's the Pacific Ocean. And on this region, we can see a series of zones in green and blue, which are showing some of the areas where there are what are called polymetallic nodules. And these are sort of tennis ball sized particles on the seafloor, these little particles down here, and they contain a number of precious metals which can be used for to help the battery industry. So with the increasing interest in developing electric cars and having renewable energy, there's an increasing need for batteries, and therefore particularly for cobalt, which is one of the metals inside these nodules. And the resources of cobalt on the seafloor in the Pacific are about 40 megatons, and there's about 220 megatons of copper. So there's a huge resource on the Pacific seafloor, and particularly in the Clarion-Clipperton zone in the mid-Pacific. There's a lot of activity going on at the moment trying to understand how to recover these nodules off the seafloor. And just as an example, at the moment, Tesla batteries, one of the electric cars, about 3% of the battery is cobalt. And so if you imagine scaling up by a factor of 100 in electric cars, there's going to be a huge need for this resource. So deep sea mining has actually been of interest for some time. And in fact, it started off in a very strange way. There was a thing called Project Azorian, and this was asserted to be deep sea mining, but it was actually set up by the CIA and Howard Hughes in the USA. So Howard Hughes was a great industrialist in the US who was extremely wealthy, and a Russian submarine sank in the Pacific, and the Americans they found it and they wanted to recover it and bring it to the surface. And they didn't want the Russians to know they were doing this, and so they set up a thing called Project Azorian, which was a whole ruse, really called a process in deep sea mining, but they were actually trying to mine this Russian submarine and bring it up to the surface. And they built a big ship which looked like a drilling rig or a mining rig, but it was actually designed to bring up this missile. In fact, they only got it part way up when it fell off again and broke in two, so it wasn't successful, but this was actually revealed by the New York Times. So that was back in 1974. But now there's actually a whole new industry developing. This is now a real industry on deep sea mining, trying to develop ways of recovering these nodules. And so the idea is that there's about 4 kilometers of water from the surface down to the region where these nodules exist. And the idea is that you'd put some pipes down and then start sucking or removing those nodules, perhaps with some tractors that'll scoop up the nodules running along the seafloor. And the nodules then are pumped up, pipe up to the ship where they're collected and then taken off for processing. And of course, on the seafloor, there's a huge amount of sediment. And that, as this tractor runs along scooping up the nodules, it's going to resuspend a huge amount of sediment. And that sediment is going to then be dispersed, carried by the turbulence, and it's going to then redeposit elsewhere. And in the middle of the Pacific, the sedimentation rate, the natural sedimentation rate is extremely slow. And so any disturbance to that sedimentation rate could have a major impact on the marine life on the seabed. And so there's a lot of interest to try and understand the range over, or the distance this sediment will travel, and also to work out, you know, how quickly it redeposits and what the zone of impact will be. If you imagine actually starting to mine in an area sort of this scale in the Pacific. So here's the US, and here's China, and so it's a very large part of the Pacific. So in order to understand this, there's a series of problems we can look at in terms of how particles move when suspended in water. And one of the key things we need to remember is if we look at the water column from the seafloor up to the surface, the water density is very stratified. So this is the density, and what you see is the density decreases with height, so it's weakly stratified. And in the top 200 meters, the water becomes much more strongly stratified as we go into the mixed layer. And the n squared, or the Brunt-Weiss-Sire frequency squared, associated with that is very small, except near the surface where it becomes much larger. Okay, so one thing you might imagine is that if the ship actually receives a lot of these nodules, and it may then remove lots of unwanted material, and it may start to put that back into the water column. Well, if it does that, then that material, we want to know where that material will go. Okay, well, very simple classic buoyant plumes. Here's a little experiment of a classic buoyant plume where we're just releasing salt water into a tank of fresh water, and what we can see is a plume sinks and entrains a lot of water as it goes down, so the flow dilutes, and we get, in a uniform environment, the plume mixes a lot of the ambient water and then spreads out on the seabed. And so that's a very simple idea about what might happen, but of course this wouldn't be salt water, it'll be particle-laden water. But if we do this in a stratified tank, a stratified ambient, of course what happens is, instead of, as this shallow water is entrained in the plume, the water here, which is fresh, moving down into the denser fluid, actually compensates for the salty water being supplied at the source, and so the flow doesn't run all the way to the base, but it intrudes at some height when the total buoyancy is depleted. So essentially, if we move through a continuously stratified zone, then the plume is arrested rather than moving to the base of the tank. And so that's an interesting guide as to what might happen if we started pumping particles into the water at the top of the sea. We might imagine they'd move down as a plume, and at some point they'd intrude just like a turbulent plume. But of course things are slightly more complex than that, and we'll have a look. But if we just take classic theory of plumes, turbulent buoyant plumes with the stratification, and we have a buoyancy flux, then the distance we'd expect this plume to sink scales with the buoyancy flux and the stratification, or the Brunt-Weiss-Sire frequency. And just by dimensional analysis, we'd expect the depth to scale with b to the quarter, n to the minus 3/4. Okay, so very simple dimensional analysis. And the pre-multiplier, which you can find through experiment, is 5. Well, if we look at the typical rates of discharge that we'd expect in this situation, we find that we'd expect the plume to sink, if we discharged it from the surface, it'll sink about 10 meters into this very stratified water, so it won't go down to the seafloor, but all these particles might end up very near the surface. And so you might imagine it might be good to put a pipe several hundred meters down into this less stratified zone down here. And if you do that, then the plume may sink about 180, 200 meters, and then it'll be arrested. And so what this shows is that it's going to be very difficult just to have a plume sink all the way to the floor of these particles because of the stratification. And so you might want to know, well, what will happen once the plume intrudes at this neutral height? So we can run another experiment, and here's an experiment where we're now releasing particles. So we have a stratified tank, it's fresh, going down to salty water, continuously stratified. We now release some particles here, very small particles. They sink down and they intrude at this neutral level. But then because the particles are heavy, they actually, as they spread out, forming an intrusion, but because they're heavy, they start settling. And as they settle, they actually fall through the water column lower down. And what you see is this very complex structure developing, but essentially it's a cylinder. So we get this cylinder of fluid developing, or particles sinking through the water column. And you can see some very fine material spreading out, forming that intrusion, like in the salt plume. But in addition to that, we now have this very interesting structure. And one thing you can notice, as well as being a cylinder, it's got a series of little ripples on the edge. Okay, and you might be interested in what those ripples are, and we'll have a look at that in a minute. And so to understand some of the basic aspects of this flow, if we consider the salt plume again, so we have our stratified water column with the fluid going from being fresh to being salty, and we release some salty water, it entrains and mixes, and it forms a neutral height at some intermediate level. Okay, and so if we look at density with depth, what you see is the density of the flow coming in is very high. As it sinks and entrains this ambient fluid, the density decreases. Eventually it reaches the ambient, it overshoots a little bit, but it then intrudes at this neutral height. So what we did is we did an experiment where we released particles with exactly the same buoyancy flux as the salt. Okay, so we generated a particle plume, and we put a bit of red fluid in this, and so we have a particle plume, and initially it sinks to exactly the same height as the blue fluid, okay, because it's got the same buoyancy flux. But what happens then is very interesting. What you see is the particles start sedimenting, forming this cylinder of particles, and the fluid, which we've dyed red, no longer spreads out at this blue layer, but it seems to rise up and spread out a bit higher up. And so one question is, can we understand that? Well, if we look at the same density picture, here's the density with depth, and here's the ambient density. So we start off in a very similar way with our dense plume, and as it sinks and entrains the fluid here, it spreads to its neutral height. So it gets to a neutral point where the density is the same. It overshoots a bit. Once it's overshot and it stops, it comes to rest, the particles fall out. And when the particles fall out, the buoyancy actually decreases because the particles are making this flow heavy. So when the particles fall, the fluid gets less and less dense. Okay? And so very differently from the salt plume, the density drops a bit more, and because it drops a bit more, when this rises back, it rises much higher than it did there. Okay? So it rises to a greater height, and that's why this intrusion of fluid from the plume is at a different height. And so one question is, can we try and estimate that height? Well, in fact, we can do a very simple calculation to estimate that height. And what we can do is, in the plume, this region up here, the volume flux in a plume with buoyancy flux B just scales, again, by dimensional analysis. The volume flux in a plume scales with the buoyancy flux and the distance. Okay, and this is a very classical result of turbulent plumes. And so the volume flux in a plume increases like the distance to the 5/3 and the buoyancy flux to the 1/3. And that's in an unstratified environment. Well, even in a stratified environment, a plume behaves, or the volume flux actually increases in a very similar way to that in an unstratified environment until we get to the neutral height. Okay, so they're very similar. So what we can do is we can combine this expression for the volume flux with an expression for the stratification. So because we've got a linear stratification, the density increases linearly with depth. And so if we work out the integral of the buoyancy or the stratification of the ambient water at any height, and the amount that we entrain, which is dq dz, so the amount you entrain at each height is just the gradient of the volume flux. If we integrate that over the height of the plume, then we get the total amount of salt we've entrained from the ambient. And when we do that, we get this number 5/8 appearing because of the 5/3. So we get this expression here for the total amount of salt. So the buoyancy that's associated with this entrained fluid is approximately equal to 5/8 of n squared h, where n is the Brunt by Sire frequency and h is the total height, which we saw before. Okay, and so that buoyancy, if we turn it round, actually means that the salt we've got in this plume, which is once the particles have gone, all that's left is the salt in this fluid. And that salt has a density that's 5/8 of the total distance the plume's gone. And so the fluid rises back to that height. And so that's why the plume spreads out at 5/8 of the initial intrusion height. Okay? And so if we do some experiments, we can look at the height and divide by this scaling for the height. And what you find is the total height is given by the white dots. A salt plume finally spreads out at 4/5 of that height, and this one spreads out at 5/8 of that height. And so the data of these experiments agrees very well with experiments. Okay? And so the first thing that's important is that if you have a plume of particles, those particles may dissolve some heavy metals and other things into the water. And so you want to know where this water is, because this is the polluted water. Okay? And we're able to track it very easily and actually get a prediction as to its height in the water column. Okay, so if you were doing this, you may think, well, can I do something different? Can I control the experiment differently? And so instead of putting in this particle plume, supplying it with fluid of that salinity, we can actually add fluid to the particles with a different salinity. And if we change the salinity of the fluid we add, supposing we make the fluid very, very salty, we'd expect the particles to go deeper. And if we make the fluid very fresh, so even fresher than the surface water, so it's got a linear stratification, it will have a density up here somewhere, then what's going to happen is we're changing the total salt in that intrusion. And so by changing the salinity of the source fluid, we can actually change the height of the intrusion. And by making the source fluid sufficiently fresh, it's possible to get this intrusion even to occur on the surface of the water. Okay? So that might be one way of trying to manage it, and then I'm trying to recover that material. So just to understand now this column of particles that are sedimenting through the water column. So we saw the plume is this top part here. The flow spreads out, and then below that we have this cylinder of particles sedimenting. And I'm asserting that these particles are sedimenting, and the reason for that is that if you suppose you take this red line, and you take a video recording of this experiment, and you plot this red line in time, what you see is this picture here. And if we go down, we see these pictures. So in these experiments, this is just a time series of that red line. Well, if you look at this time series, what you see is there's a series of lines in this direction. And those lines are parallel to the white line. And the white line is a line which has the fall speed of the particles. Okay, so if the particles just fell out under their own Stokes fall speed, the height would decrease with time according to this white line. And so what we can see is all the structures are moving down through the tank with a speed equal to the fall speed. Okay, so I don't think there's not very much fluid convection going on here. There's no water being carried up and down. It's just particles sedimenting. And you can see a similar effect if you take the blue line at the edge. Again, you can see these lines coming down. Okay, so if you think that's the case, then if we measured the concentration of particles in this cloud, what we'd expect is that the flux of particles arriving, which would be the source flux of particles, so the volume flux times the concentration, that should equal the radius of this cylinder, or the area of the cylinder, pi r squared, times the fall speed, times the concentration at this neutral cloud. And the concentration in the neutral cloud just corresponds to the concentration of the source multiplied by the ratio of the volume flux at the source to the volume flux at the neutral cloud. Okay? And so from this we can predict the radius, and the radius follows this theory very accurately. And so that supports this idea that these particles are just sedimenting. And that's very interesting because it means once this initial convection's occurred, the stratification stops any more particle convection and we just get sedimentation. But you might be asked, and just to sort of try and reiterate that, if we put some lines of dye in our tank. So this is the stratified tank, and we've just injected dye at different layers, red and green and red dye at different layers in the tank. And we then have our particle plume here, this cylinder. So here's the plume, the neutral height, and then the cylinder. And what we've done is this is now the blue line. And what we're seeing on this blue line is a time series of the blue line. So time moves forward, and we're just plotting that blue line as the experiment runs on. And what you see are, again, these lines here which correspond to the sedimentation. And you see after the experiment's finished, when all the particles have fallen out, the tank is essentially undisturbed, but there's very little dye down here. And so there's been very little movement of fluid. Okay? So there's a lot of movement in the plume, but then below that, there's very little fluid motion. Okay, so the particle's just sediment. So one question is, what are these ripples? What's going on with all these ripples on the edge of the structure? Well, if you think very simply about this, we have a column here of particles sedimenting through a stratified layer of water. So the density here is a little bit bigger than the density there because there's some particles present in the fluid. And that tries to make this fluid convect downwards a bit relative to the surrounding fluid. But if the fluid starts moving down, it then remembers there's stratification out here, and so it can't go very far, and it needs to then stop, and so it spreads out. And so you get a little circulation pattern forming, and as that circulation pattern forms, you get these little ripples at the edge of the plume, and the particles sediment through these ripples, so these ripples actually move up as waves through the structure. And if we go back to this time series, you can see these structures moving up with a very small speed, and they're actually these waves on the edge of the plume moving upwards. And there's a balance between the convective recirculation and the fall speed that causes these ripples to move upwards. Okay? And we can get their spacing and their speed just by simple scaling arguments. Okay, so that's sort of an insight into particle plumes. Well, some of those ideas carry through to bubble plumes or droplet plumes. Okay, so if we go back to the problem at the beginning of a blowout in the deep sea, in a blowout in the deep sea, so this is an example from the Gulf of Mexico where there was some data showing an increase in concentration of a few hundred meters above the seafloor. And if you think about what's going on, if we have a salt plume now, so now we have a stratified tank and we release fresh water at the bottom of the tank and it rises up and forms an intrusion. If we do the same thing but instead we release droplets, and these are droplets of oil, so this is vegetable oil, but you could do the same thing with bubbles. If you do that experiment, what happens is, again, it rises to the same height, but then the droplets separate, and the droplets are all dyed blue here, and when those droplets separate, the water that's left behind finds itself denser, and so it sinks back down a little bit. And again, it's this 5/8 magic number, which tells you where this intrudes. And so we can actually predict where the water goes from this plume. But often in these situations, the water column is stratified in more like a two-layer system. So we have the deep ocean and then the shallow ocean, and there may be a sort of jump in the stratification. And so to model that, we can look at bubble plumes rising through a system where we have a dense fluid and then a less dense fluid. And so now we have a bubble plume rising through this, and we dye the lower layer red. So this is dense salty water, this is fresh water, and we just release bubbles now at the base of this tank. And when we do this, what we find is if we have a sufficiently large flux of bubbles, then the plume rises all the way to the top of the tank, and you can see here, and it carries some of the red fluid up with it. Okay? And so the red fluid is mixed all the way to the top of the tank, and then because the bubbles separate into the air, this fluid is heavy compared to the top layer, and so it falls back down again. Okay, and we get an intrusion somewhere in this upper layer, or the fluid may sink back down to the interface. But if we have a small flux of bubbles, so the plume is a lot weaker, what then happens is very interesting. And what happens is the plume arrives at the interface and it carries on through, the bubbles carry on rising, but now the water in this plume is actually salty water that's heavy compared to the fresh water, and the mixture of salt water and bubbles is now heavier than the density of the surrounding fluid, and so it can't carry on rising. And so instead what happens is it stops and it sinks and spreads out at that level. Okay? And so, but as it does so, it mixes some of this water and we get a mixed layer forming at the interface. And you might be very interested in how quickly that mixed layer forms. So the first thing you can do is you can take a volume flux of the plume. We've seen just from our simple scaling laws, the volume flux scales like the buoyancy flux to the third times height to the 5/3. And in a bubble plume, in this uniform lower layer, the buoyancy flux is conserved. Okay? And so we can work out the buoyancy of our flow, and the buoyancy of the flow is just the total buoyancy flux divided by the volume flux. And so what we predict is in this lower layer, the buoyancy or the density difference of our flow essentially decreases like height to the 5/3. And so what that means is that depending on where this interface is, the flow may be denser or less dense than the top layer. And so we've done a series of experiments where, using plume theory, we predicted that the flow was less dense than the upper layer, shown by these green squares. And we did other experiments where the plume theory predicted this plume with the salty water was more dense than the upper layer, shown by these red dots. And when the value is 1, it's got the same density as the upper layer. And what you find is that you get plumes with in the squares, and you get fountains, two-phase fountains in this case here. And this fountain is essentially a fountain that's driven upwards. It's a dense flow, it's got buoyant bubbles in, but it's got heavy salt water that sinks back down and spreads out at the interface. Okay? And if we want to work out the mixing that produces, what you can do is if you take a video of the experiment and we put the red dye in, we can see that red dye mixing into the fresh water and generating an interface zone between the two fluids. And so our fountain in time basically keeps on making this mixed hybrid zone. And here's a time series showing the entrainment is showing the deepening of this mixed layer, and this front here is showing the fresh water, or sorry, the salty water, the pure salt water layer being taken down and entrained into the plume. And so we get this mixed zone forming by this bubble plume. And so if you're interested in mixing a water reservoir, which can get stratified in the summer, or you're interested in mixing lakes, I guess they've done experiments in Lake Geneva trying to mix up lakes. This is actually showing you what happens if the bubble plume doesn't bring fluid all the way to the surface, but actually mixes the interior. And it's very interesting just having a look at what's going on at an early stage at the interface. So here's the interface, and what we see is that the fluid, the red fluid rises up, stops, and then it sinks back down again and spreads out. If we remove the dye, you can see the bubbles carry on rising. These black dots are the bubbles, and they form almost like a cylinder here. And so we've got this structure in the top layer where we're getting the bubbles carrying on rising, but no fluid being carried. And if we again use our simple plume theory, we know the buoyancy of the flow at the interface, and we know the speed of the flow at the interface, just using simple plume theory by dimensional scalings. And so we can work out a Froude number, or if you like, a ratio of the kinetic energy to the potential energy using the radius of the plume and just taking the square root of that. And if we want to know the height of rise of the fountain, how high does this rise before it sinks back down again, you might imagine there's a balance between the kinetic and potential energy. And so if we assume there's a balance, that the height of rise just scales like u squared over g primed, that means the height of rise scales like the Froude number squared. Okay? And if you test that scaling with data, you see it fits very well. And the reason you want to know how high this fountain rises is because that's where all the mixing's happening. And the mixing will be proportional to the height of rise of that fountain. And in fact, we can see that because if we work out the entrainment coefficient, just in our formula for how quickly we grow a deep layer, the mixed layer, we see the entrainment coefficient just scales with the Froude number squared, just as we predicted. Okay, so these ideas about separation of particles also have relevance in other situations. So I mentioned volcanoes. Now, one of the very odd things about volcanic plumes, if you look at them, and I think you can see in all these three photographs, is that they're different from an experiment using fresh water rising through salt water. So when you have a salt stratified tank, what we see is fresh water, the plume rises up and intrudes, and it forms what's quite a symmetric intrusion. Okay? But if we look at these flows here, they're actually looking more like cones, and they seem to be rising up through the air. Okay? Again, this one has a different angle, and this one again. So they have more like a flat top, but they actually have a cone structure on the bottom. And that's quite different from this structure here. Okay? And so one question is, why is this difference occurring? And if you look at the typical size of the particles in this intrusion, it turns out these particles will start sedimenting out over tens or hundreds of kilometers. And these clouds are spreading, this is of order 30 or 40 kilometers, and they're spreading out and sedimenting out particles. Well, as the particles fall out, the pumice and the ash falls out, the air that's left behind, which is hot, finds itself a bit more buoyant. And so it carries on rising. Okay? And because it carries on rising, this neutral cloud doesn't just spread out, but it actually rises up. And so to model that, we can do some more experiments where we take a plume, and now we take a plume of fresh water and particles, and we have the same buoyancy flux as in the simple salt plume, so it rises to the same height. But as it starts to spread out, the particles start falling out, and the fluid realizes it's a bit less dense now because some of the buoyancy was associated with the particles, and if you remove them, what's left is less dense, and so the intrusion starts at a greater height, and we get this anvil shape, very different shape of intrusion forming, even though the buoyancy flux is the same as in these salt experiments. And so some of these interesting structures are associated with the separation of the particles from the flow. But I wanted now to turn in the last 10-15 minutes or so to problems of infection dispersal and some problems of fountains. So we talked about plumes, but I wanted to talk about the problem of having droplets carried in plumes and jets, and what we might do in terms of public health. Well, there's a lot of airborne infection, or thought to be airborne infection transmission, particularly tuberculosis and SARS, and when people cough out, they tend to release a whole series of little droplets. And people have done a lot of experiments measuring the distribution of sizes of droplets, and they tend to be very small, of order a micron or smaller, and so they have full speeds down to 0.1 millimeters a second. And what you might be interested in if you're trying to design ventilation for this system to get rid of these droplets is to understand how far they're carried in these flows. And there's two sorts of generic designs hospitals develop. One is where you've got a patient who's got a disease and you don't want any of their infection to escape, and so you negatively pressure the room, and with the negative pressure in the room, then the idea is that none of those droplets can escape. But if you've got a patient who's got immunosuppression, you don't want them to receive any air from outside, so you positively pressure their room so the air goes elsewhere. Okay, so there's two different sorts of design, and but of course, every time you open the door, you're actually getting exchange between the spaces, and also you're going to have to supply air from some vents at the surface, at the ceiling or the floor, and so there's a lot of interest in understanding how this air carries the particles. And there's a whole class of other hospitals which are naturally ventilated, very old hospitals, where air tends to come through floor ducts, and so there may be cooling plena, and then air comes in and then rises up through the space. And so we've done some work trying to understand what happens in a very simple design where we have a plume in a confined space and the plume containing some particles. Okay? And what the idea is here, so this is an example where we're essentially having some chiller system or some cooling system here which has a source of infectious particles too that are carried down in this cold plume, and that draws in air through a high level inflow, and there's cold flow leaving. And in this situation, if we have a cold source of fluid, air conditioning in the lower part of the space, then what happens is, because the plume entrains all this air coming in, at some point the volume flux in the plume will match the volume flux coming in through the opening. And when the volume flux through the plume matches the volume flux coming in through the opening, we get an interface, and all the flow occurs through the plume. If we go to lower points in the space, then the volume flux in the plume exceeds the volume flux in this lower part of the space, and so we actually get a return flow. in this region, and then the flow leaves, we get this cold outflow. So if we now think, well, what happens to the particles? If we release particles in this flow, the particles come down and they get circulated around in this plume, and they rise back up again in this backflow. And as they rise back up in the backflow, eventually they remember they've got a fall speed, okay? And they've got some very small fall speed, so they don't get right to this static interface, but they stay at they get to some other height. And once they get to that height, they then mix up in this lower layer. And so you can run an experiment to show this. So here's an experiment where we have a tank full of fresh water, and we supply salt water, which is a model of cold water, but we put some particles in. And these images are just showing where the particles are. And red is high concentration, blue is low concentration. And we see that the concentration is very low in the plume because it's mixing so much. But with time, what happens is we get this lower layer beginning to fill up with particles. Particles are being extracted, but they're also filling up the space. And eventually we get a stratified zone where we get clear air with no particles in. And then the lower zone is actually all well mixed, and it's laterally well mixed by this convective flow. And so there's extremely effective dispersal produced by these ventilation flows. And if you sort of measure the concentration of particles with height, you see there's a stratified zone, and there's a zone down here where it's very, very highly concentrated. And this, of course, is where all the patients are, so this may not be a great design if you're supplying some infection here by mistake at the top. And to work out the height of that interface, we can just appeal to simple plume theory. So the height of the fluid-fluid interface, the hot-cold interface, just comes by matching the volume flux in the plume with the ventilation flow. So we've got a ventilation flow Q, and the volume flux in the plume scales with the distance from the top, and so that gives you a height. But of course, the layer of suspended particles also knows about the fall speed, and so when we're making this balance to work out the height of the particles, we actually have to include Q plus AVS, which is the fall speed of the particles. And then we can estimate the depth of the particle filled zone. And that agrees well with experiments. But we can also imagine a situation where we have heating, or imagine a patient sitting here coughing out, producing a plume of hot air that rises up, and we want to know where do all the particles go. And so if we reverse the problem and have the hot air rising, then what's going to happen is that hot air generates a plume, and it entrains the surrounding fluid, and so all the ventilation flow gets entrained and carried up and then vents out the top of the space. Okay? And now there's two interesting situations, because what happens to the particles depends on the fall speed of the particles compared to the flow speed of the ventilation spread out over the whole space. So we've got this very slow upward ventilation going up here, and we've got particles trying to fall back out again. And so if the ventilation flow is smaller than the fall speed of the particles will rain out again and they'll fall back down. Okay? But if the ventilation flow is bigger, the particles will be carried out and they'll vent from the space. Okay? And so this gives you an estimate for the minimum ventilation to remove all these particles. Okay? Because they get carried up in the plume and then they find themselves in this very slow flow. Well, of course, if they fall out, when they fall out, they may get re-entrained into the plume. And it turns out that the area over which you can re-entrain particles exactly equals the ventilation flow. And so, whoops, I'll just press on. So what happens is, if we model how particles sediment from the bottom of this top layer, the particles fall out vertically with their fall speed. They get entrained into the plume by this entrainment flow, so the plume is entraining this fluid, and so we've got a rate of change of height and a rate of change of radius, and if we combine those, we can work out how the radius changes with height, and there's a critical radius for particles when they can get re-entrained. And that critical radius is basically given by pi r squared critical is equal to the volume flux divided by the fall speed. Okay? And that's exactly the condition we had a minute ago, that the particles are vented from the top of the space. And so if the ventilation flow is smaller than that, you will indeed sediment some particles. Otherwise, all the particles get vented from the top of the space. Okay, and so this gives you some guidelines, just these very simple calculations on how to ventilate these sort of spaces. I think if I've got 5 minutes left, is that okay? 5 minutes, okay. So I thought I'd just finish by talking about one more problem we've been very interested in about particle turbulence and particle-laden flows, and these are related to volcanic flows or turbidity flows where we have particles in suspension. And but if we think about a volcanic flow here, sometimes a volcanic flow comes out of the volcanic vent and it entrains air and it becomes buoyant by heating up the air, and it lifts off and carries on rising. But sometimes the flow comes out of the volcano as a very dense mixture and produces a dense fountain. And so there's a lot of interest in understanding how dense fountains work when they're filled with heavy particles. Okay? Because we know that a fountain will rise up to a certain height, okay? And at that height it'll have a characteristic speed, and then it'll collapse back down again. And there's an important question about how the speed of the fountain compares to the speed of the particles, their fall speed. So if the fall speed of the particles exceeds the fall speed of the fountain, you'd expect them to fall out before you get to the maximum height. And that's going to change the whole dynamics. Okay? And so we can have a look at that. So I can just show you, here's a picture of here's a movie of a classic fountain. And so that's how a fountain works. It's buoyant fluid is coming up, and it rises to a maximum height. It then remembers it's heavy, so it's momentum driven, remembers it's heavy, and it falls back down again. And so we get this convective flow where we get parcels of fluid accumulating here and then falling back down again because they're heavy. Okay? And we now want to look at how does this flow change if we put particles in. Okay, so if we just look at a simple flow, what you see is if you take a line down the middle of the tank, you can see lines coming up where the flow is going up, and then lines coming down where we're getting this flow sinking off the edge of the plume. But if we have a particle plume, so in this case, instead of putting in salty water into a tank of fresh water, we put in particle-laden fresh water into a tank of fresh water. Okay, what happens is that this is showing you the particles, and this is showing you the fluid, in the case that the fountain speed, or the speed of this fountain, is much bigger than the full speed of the particles. And what happens is the fountain reaches that maximum height, and then it collapses because it's fallen to zero, and both the particles and the fluid fall back to the ground. But in the case where the full speed of the particles is bigger than the fountain speed, then if we look at the particles, they don't rise as high. The height is somewhere down here, and they fall out, and when they fall out, the fluid keeps on going. And so we get a separated flow. And so there's a total change in the type of flow that occurs depending on the fountain speed compared to the fall speed. And the typical fountain speed depends on the momentum flux and the buoyancy flux. Okay, so if the buoyancy flux is bigger, or the momentum flux is bigger, the speed is smaller, and the buoyancy flux is increases. And so you can actually look at the height of the fountain compared to a reference fountain as a function of this fall speed over the fountain speed. And what you find is that if the fountain speed is of order 1 times the fall speed, then the fountains are very similar to a normal salt fountain. But once the fall speed starts increasing to greater values, the height of the fountain actually starts decreasing, and the fluid separates and keeps on rising. And you can see this in the structure of the fountain. So this is a normal fountain where there's a lot of oscillation at the top of the fountain. And this is a fountain where the full speed is bigger than the fountain speed, and so the particles don't get that high, and they actually fall out again. And we see these ballistic trajectories of particles as they start raining out the fountain. Okay? And what's very interesting is that if we go back to the volcanic case, we can then start thinking, well, what happens if we have particles and salt in this fountain? So just to finish, I thought I'd show some interesting results where we have a tank full of, so we've got a salty tank, this is salty water, and we have fresh fluid plus particles being released, and there's enough particles that the mixture of fresh fluid plus particles is dense compared to the salty water. Okay? And so it comes out and it forms a fountain, and then it tries to collapse. Okay, and if you have a very small, so once this collapses, it falls back down to ground. Okay, and so this is in the case where, in order to so it starts sinking. But if you imagine increasing the salinity of this ambient fluid, okay, making this saltier and saltier, then when you come to this rest point, just before the flow collapses, some particles will sediment. And those particles will relieve behind the fresh water, and that fresh water may then carry on rising. Okay? And as you make the salinity bigger and bigger, you can get more and more of the flow actually rising to the top. So you get a transition from having a fountain that stops and collapses to one that actually rises up and gets all the way to the top of the system. And if you do a time series of this, what you can see is the flow comes in and it stops, some of it collapses back down again, and some of it carries on rising. So we get this very interesting pattern. And so essentially that's what's shown here. We get full collapse if we have extremely salty ambient, but as the salt content of the ambient becomes closer and closer to the particle content, so that you only need to sediment a few particles to change the buoyancy, then more and more of the flow is actually able to turn into a plume and rise up. And so this is really an example of how a volcano works. So what happens is you get close to the height of the fountain, particles separate from the rest of the flow, and the rest of the flow carries on rising, forming a big eruption plume that's buoyant, and this material actually sinks back down to the ground. And this just shows a systematic change as we have to, so as we move along this line, we need to sediment fewer and fewer particles to generate buoyancy. Okay, so that's probably a good place to stop. And so what I've tried to do in this talk is go through a series of real problems of deep sea mining, problems of volcanic eruptions, problems of air, of infection dispersal in buildings, and show you how we can do very simple experiments using plumes or using jets, negatively buoyant jets, to understand some of the controls on these flows in terms of when do the particles remain with the fluid, when do they separate from the fluid and start sedimenting under their Stokes fall speed. And you can see there's some very complex relationships, but ultimately the critical number in all these problems is the ratio of the convective speed of the bulk mixture compared to the fall speed. And as you move through that from being greater to smaller than 1, the overall structure of the flow can change quite fundamentally. And I think we've seen that in a number of different examples. So I'd be happy to take any questions. Is there any questions? Thank you for your attention.